Welcome to this session on quantum computing, a new realistic paradigm. We're going to start in 2 minutes when I'll introduce the speakers, Prashant and Cherry. So we have Prashant here. I'm just going to quickly introduce both of you. Welcome. It's good to have you here, and it's a pleasure. Thank you for being part of the B-Side 8 meeting 2021. So here we go. Prashant is a senior cybersecurity advisor for Fortune 500. He has a bachelor's and master's degree in IT from India and over 14 years of Canadian IT working experience in various verticals, industry verticals. He's a geek, like he likes to call himself, with a purpose, and likes to support the development of talents. He likes to share his experience and to continue to support the progress of cybersecurity discipline. He considers himself a problem solver to solve interesting IT problems, not just cybersecurity. He plays chess, loves to hike and camp in the mountains alone, and ponder over the purpose of life and nature. Welcome, Prashant. It's good to have you. Great. And then the second speaker is Cherry. Cherry is currently working as a visiting student researcher with the Institute of Quantum Science and Technology, University of Calgary, Alberta. Her research interests include network security, quantum computing, quantum security, and quantum cryptography. She received the Bachelor of Computer Applications degree from SSD Women's Institute of Technology, Bathinda, India, in 2014, and Master's in Computer Applications degree from Punjabi University, Patiala, India, in 2017. She's currently pursuing a PhD degree from Chitkara University, Rajpura, India, since 2019, in computer science and engineering. It's my pleasure to have you as well, Cherry. The stage is yours. You're mute, Cherry. Can you unmute yourself? Prashant, can you try talking because I can't hear Cherry?
Hello, can you hear me now?
Yes, I can hear you, Prashant. Cherry, can we hear you? Can you speak as well? Cherry, you need to unmute your mic. It still shows as muted. Prashant, can you speak again?
Good.
Okay, great.
Jerry, you may have to select your video or audio in there. How about you can try that on the backstage while I continue the presentation? Maybe it's your mic, and then we can come back to your slides. And if you can, then we will improvise. So welcome everybody on this presentation on quantum computing. I hope I'm sharing my slides. I hope you all can see it. And thanks for the good introduction to Cherry and myself from Sherifat. Today's talk will be a mix of philosophy. It'll be a mix of metaphysics. It'll be a mix of what's happening in quantum computing, as well as what are some of the real applications in this industry as we speak. So it is not a talk which is just a philosophical scientific talk. It is more down into the weeds when we go to the later stages of the talk into what quantum computing is actually doing in the real industry today. But from me, you will get a dose of philosophy. So stay tuned. So theme of the talk, we'll talk about building blocks of matter, particles. So there'll be a dose of physics, and please put your question answers in the session. We'll try to put 10 minutes in the end of the presentation to cater to Q&A. We'll talk about the great debate on quantum mechanics. It's a little bit of metaphysics. This debate happened between Albert Einstein and Niels Bohr. And there is a purpose for this debate into why we are making this theme down into what quantum computing is all about. We'll talk about some fundamental principles of quantum mechanics. For those who have been physics students in their college days, or those who like physics, this is a little bit of dose of what happens in quantum mechanics even today. One wise man in quantum mechanics said, "You have not learned it if it has not confused you." So I'll try to confuse you guys today. I hope I do a good job in doing that. And if I do that, do give me a thumbs up in the end. So we'll talk about certain principles of quantum mechanics and where quantum mechanics or physics meets computing sciences, the Moore's law, and why is that relevant, and why Moore's law is leading to breakthroughs into quantum computing. We'll talk about what quantum information theory is, or what quantum informatics is, and that's where Cherry will take on if she can fix her mic issues. We'll also talk about certain practical applications in the industry today, in the world, in US, Canada, here in Alberta, where actually there's work going on in quantum computing. In the University of Calgary was the logo which showed you before. So I'll try to make it fun, and I made some these small tidbits out here. So what you see out there is the light cone on the left side. This is actually the future. This is actually the past. So you can Google it if you want. This is Einstein's theory of relativity. There is a light cone at a 45-degree angle. All world events happen within this future cone, and all past events had happened in this past cone. Anything beyond a 45-degree angle means you're moving faster than the speed of light, which is a different realm altogether. If anybody's interested, I can talk to it afterwards. They're called tachyons in the world. And put your light bulbs on. Let's have an idea. Let's figure out why this is a tinkling industry, why it's a field. And I'd like to tinkle your minds to it. All right. Can particle physics explain universe? So, I got this small microscope out here with me. So you can go to the extent of the universe in the powers of 10, as you see on the far right here. You move from planets over to galaxies, over to superstars, over to supernovas, over to, dwarf stars, neutron stars, and whatnot. I do see you, Cherry, online. If you may say just hi to confirm.
Hi.
Good.
Okay.
So that's particle physics. It takes you right up to the edges of the universe. And then there is the other side of the equation, which is subatomic particles going into, the atoms and the protons and the neutrons and the nucleus, right up to quarks and leptons. So, just to give you an idea, you can go as deeper as you want, or you can expand as much as you want. The beauty is, if you see this diagram, I was kind of reflecting on it before this presentation. The patterns in general in the nature repeat themselves. If you see the patterns of a solar system, a similar pattern exists in an atom, where you have a nucleus and you have electrons revolving around them. You have a sun, you have planets revolving around them in orbits. Yes, there is difference of physics between the two, but the idea here is there is a whole gamut of physics out there called particle physics, which leads into quantum mechanics, and it leads into classical physics, and I'll come to that. But keep that in mind. Once Newton was asked, do you think this is all random out in the world? He said, no, nothing is random in this world. His idea was classical physics. There must be a creator who has created all this, because it is such a precision out there. If you can change the electron's negativity, or which is 10 to the power minus 19 coulomb, this is its well-defined study, to 10 to the power minus 20 coulomb, nature will not exist, we humans will not exist. That's the kind of precision we have in an electron with its negative charge, which runs the universe. So keep that in mind. The great Einstein-Bohr debate. So Albert Einstein and Niels Bohr, we all know Einstein is quite famous for his E equals to mc square equation. He was quite of an outspoken guy, and he once said, great spirits have often encountered violent opposition from mediocre minds. And he actually told it to Niels Bohr, who was one of the stalwarts of quantum mechanics. So you could see the kind of constructive debate, but the kind of being at loggerheads with each other. I'll come to exactly what the debate between Einstein and Bohr is, because that actually spawned the field of quantum mechanics and quantum computing and quantum physics, and why it's a field in itself and how it is leading to breakthroughs in computing in today's era. But a very interesting comment, right? I mean, he talked about spirits, and he's talking Niels Bohr as a mind. So spirits are always bigger than minds because they can control matter. We all can, go into philosophy, what is a spirit, what is mind, and what is metaphysics. But very interesting comment out there. Niels Bohr, Albert Einstein, God does not play dice with the universe. That's what Einstein said, that God is not randomly acting in the universe out there. And what Niels Bohr said, God not only plays dice with the universe, but he puts them into corners where they cannot be seen. So God does not play dice with the universe. God not only plays dice with the universe, but he puts it into corners where they cannot be seen. A very interesting conundrum. When you see physics and when you see metaphysics, there is Einstein who is saying everything is deterministic. You can propose there is a cause and effect. And Bohr is saying there could be a cause, but there could be multiple effects. Or we cannot actually pinpoint the actual cause of those effects. And that's where the world of quantum mechanics play a role. So very interesting metaphysical debate, actually. Another interesting one, think of it for a second when I say it. Reality is what is observed. Bohr said reality is what is observed. When I take this magnifying glass, I'm looking at you, I'm looking at everybody out here or at my presentation. I can see you, you are a reality for me. Einstein said reality is what it is. Even if I'm not looking at you, or that tree has fallen in the forest, that tree still exists. Without me looking at that tree still exists. Bohr said, no, that tree does not exist for you because you have not yet observed that tree in the forest. So beautiful. And that's where quantum mechanics will play a role, and will come to when you do a measurement on a system, that's when it becomes a reality. Before that, it has multiple states out there in the quantum realm. Philosophy, going back into physics, and then literally going into computing sciences, we'll talk about. What is quantum mechanics? It's a complete physical theory in itself. You can Google if you like what's a complete physical theory. There is a mathematical theorem called Gödel's paradox, or Gödel's theorem, which states it's hard to have a physical theory which can explain everything in the universe. Many of you are computing sciences students. You may have heard what's called Turing machines. Turing machines are like, if there is a machine out there, and as a human being, if they're all both in the black box and you pose questions to us, if the machine is giving answers to me as a human, I'm giving answers equivalently similar in the black box, then you can say there is actually an artificial intelligent computing device out there, because you cannot find the differentiation between a human being giving the same answers versus the machine giving the same answers. So, the idea of physical theory is very interesting. So quantum mechanics has all the gamuts and all the physics and mathematics behind it. And now it is going into the realm of, computing sciences, how you make application and software. We'll come to actual examples. And I'll probably, after when Cherry presents, I'll probably post some links out there. Google, Microsoft, they have actual quantum software you can go in and play with and create your algorithms around. Quantum mechanics is based on four mathematical postulates which lay the ground rules for our description of the world. I won't go into the full detail of what those mathematical postulates are, but an interesting one on Newtonian gravitation. So I have this apple with me. Newton said, this apple falls, there is gravity which is putting it down. This is deterministic. An apple went down, it came down exactly in the trajectory it was expected to be based on the gravitational force. This is classical mechanics. Newton's three laws of motion talks about how it falls down in a deterministic fashion. Imagine for a second this becomes a subatomic particle. It goes up, and now you cannot actually say how it is falling like this. There is a possibility it is falling like this. There is a possibility it is falling like this. There is a possibility it is falling like this, until it falls at a fundamental location where you observe and say, oh yeah, it has come here. So from the origin to the destination, there are multiple paths through a quantum mechanical tunnels or in that realm, which can take you to that. That's the fundamental difference you see between what Newton said versus what quantum mechanics is bringing up. What Einstein said, God does not play dice with the universe, and what Bohr said, no, it can go multiple paths and can still reach to the same conclusion. Schrodinger's cat paradox. Many of you may have heard of this one, but a very interesting conundrum. So what Schrodinger says is this. You have a subatomic particle, a radioactive generator here, and there is a 50-50 probability in the quantum world, as we call it, which can fire a particle, which can lead to this handle having a 50-50 probability that it is going to either drop or it is not going to drop, which leads to a 50-50 probability that the hammer is going to hit the poison box here, a jar here, which leads to a 50-50 possibility that the cat is alive or dead within the Schrodinger box. You see, what has happened from a quantum mechanical realm, which is subatomic in nature, right up to the classical realm where you have a big cat out there. Now, it doesn't behoove physics. It doesn't behoove logic. If you ask me, how can a cat be dead and alive at the same time? It is either dead or alive. But the beauty is, in his paradox, this is what Einstein said. Either the cat is dead or it is alive. You don't know, but it has either of both states. Bohr said, no, you look into the box. When you look into the box, your act of observation at the cat makes it either into a dead or an alive state. So it's the observer which leads to the determination of a measurement of a system. Very beautiful concept. An observer leads to reality. Some folks say take observer out of the picture, reality is what it is. So very interesting conundrum in how superposition plays a role in quantum world. The uncertainty principle. So again, interesting one. You have this apple. This apple is literally lying right here. What is its momentum? For the guys who have known physics, its momentum is 0. And I can tell its position. I can literally count from the wall down here and say, what is the position of this? So the position and momentum of this classical object can be known at the same time. What Heisenberg said, in the quantum world, when you make it so small that either you can identify the momentum of this, then you can't tell what the position is. Or if you're looking at the position, then you can't tell what the momentum is. If it is moving, I can either tell the position or I can tell the momentum, but not both at the same time. Another beautiful concept. And that leads to this, what people think, how can I wrap my brain around? Like, it feels fuzzy to me what quantum mechanics is. These are the principles which lead to that fuzziness. Like, you cannot have two attributes identified at the same time in the quantum world, which you could do in the classical world. And these are some fundamental principles because they actually relay in quantum cryptography and how they make quantum cryptography secure 100%, because you cannot break the laws of physics. This is not a computational problem where you could compute with enough resources and say, now I can break it because I can give enough money, power, and time to a computing system to do that. No, you're going to falsify the laws of physics if you break a quantum cryptographic channel without observing it. And unless you have a new physical law which is replacing that one, it is fundamentally not possible. So those are some of the security aspects of what what some of these principles bring to the table. Uh, de Broglie's matter in wave equation. So I have this another one. You have a magnet. These magnets, they talk to each other. In the quantum world, either there is a particle which can behave like a wave, or a wave can behave like a particle. You have this magnet, and why is this magnet connecting to it? Because there are magnetic waves which go north south, and these magnetic waves actually connect, and they attract each other. So in the quantum world, these magnetic waves can behave like particles, and particles can behave like magnetic waves. There's actually a term for that. You could Google in for gravitational waves, as they call it in classical physics. There is a particle version of it called gravitons. For light, there is a wave version of it, which we all know light is a wave. In quantum mechanics, there is a term for, there's a particle version of light called photons, we all know about. So matter can either exist as a particle or as a wave, depending on how you want to interpret that for your particular situation. Another very beautiful concept. It's hard to wrap your brain around, how can an apple be a wave? It can either, it is a solid particle, it's a solid matter. But in the world of quantum mechanics, that blurs. Einstein-Podolsky-Rosen paradox, another interesting one. So you have these, imagine you have these two particles, which are in my case two dices. So this paradox was brought by Einstein to falsify quantum mechanics. It's a very interesting paradox. That's why they call it a paradox. They call it spooky action at a distance. So you have this one particle. Imagine this is one particle. It implodes, and these two particles start moving to the ends of the universe. They keep moving to the ends of the universe. Now imagine these are the ends of the universe. So if you all know from physics, this is called the law of conservation of momentum. What was initially at a zero momentum state, fundamentally the whole system would be at zero. So if it is going at plus 15 kilometers per hour, this is going at minus 15 kilometers per hour. So there's still the total momentum of the system is zero, because the original was zero. The system's, the total momentum plus minus will also be zero. Now what Einstein said, you have a particle, it breaks, it goes into two ends of the universe. Two ends of the universe. Now imagine that. So if I do something to this particle, what will happen here? Einstein said that if I do something to this particle, if I make it say up, this particle will go down, because the conservation of momentum says that it always has to be zero. And this happens instantaneously because the law of physics cannot be broken. Bohr said, how can that be possible? Einstein said, how can that be possible when how does this particle know, until this particle sends a signal at the speed of light to this particle and say, hey, I'm in the up state, you got to go in the down state. And that is not an instantaneous action. In the ends of the universe, it's probably take light years before this signal will go to this particle and say, I am up, buddy, you got to go down. But in reality, scientists have done experiments where they see instantaneously this communication happening at shorter distances. But this is beyond imagination. You're breaking the fundamental barrier of velocity of light, which states that it takes time to get a signal from one place to another. That's Einstein's theory. Bohr said, no, this is one system. This is just one system. Whatever you do here, this instantaneously will take a hit on it. So you consider this as one system. Very, very counterintuitive sometimes, but this is actually proven in experiments. They call it the quantum entanglement experiment, and probably Cherry will talk about some fundamental applications of that. This has been proven in the lab. Beam me up, Scotty. Captain Clark, Star Wars, says, Scott, beam me up. Is teleportation possible? This is actually what teleportation is. Fundamentally, instantaneously, you're sending a signal and something happens here. You're literally teleporting a state or a signal from one place to another. If you could do that on the particle level, future is your take. In future, you may bring it up to a point where we as humans can get teleported, and you never know. When human mind puts their brain around certain things, they can achieve that. So it is not fiction. It can become reality. In the lab, it has become reality for particles. Moore's law. So what is Moore's law? Moore's law is fundamentally It's a statistical law. It's not any physical law by any means. You can all Google it. It states that on a chip, on a microchip or a processor, the transistor capacity, which runs the zeros and ones, doubles every 2 years, precisely every 18 months, but every 2 years, the transistor capacity, the density of the transistors doubles every 2 years. So you're putting more and more transistors, which are actually doing, binary calculations on the same area, unit area, if you will, on the same chip, and that is increasing fundamentally the processing power of the chips. Now imagine for a second, these transistors have to become smaller and smaller so that they go into exactly the same unit area for that particular chip. There will come a time when these transistors will go at the level of atoms and molecules and electrons, because they have to go to that level if you have to continue the Moore's law. There will come a time when the Moore's law will lead to quantum computing, where the laws of classical physics, which I've been talking about right now, move into the world of quantum mechanics. You can't avoid it. If you continue to need to get more power and processing from a chip, and you're reducing it down, then those transistors are becoming smaller and smaller to the level that they become at the level of quantum mechanics. Classical mechanics will not play a role. So your classical theory of bits and bytes and zeros and ones, 5 volt and 0 volt, would be broken, and you will go into the field of quantum computing and qubits, which is what my co-presenter Cherry will talk about. My last slide, then Cherry will take on from here. It talks about quantum mechanics as a field of physics moving into different areas which are still physical in nature, or experiments they are doing in concepts I was talking about, EPR paradox and Einstein-Podolsky-Rosen paradox, superposition principle, Schrödinger-Cat paradox, etc. They're using these systems, these concepts, into quantum key distribution, quantum algorithms, quantum computer, quantum error correction. You can actually error correct bits the way we do error correction on integrity hashes, for example. You can do those error corrections on bits, data compression. So they're moving into the field of information theory and finally into the field of practical applications of quantum computing. So I'll stop there and I'll continue controlling the presentation. But Cherry, if you can come online, please.
Yeah, am I audible now?
Yes, you're audible, Cherry. Go ahead.
Oh, thank you. Okay, so thank you, Prashant. So I'll not take much time. So starting with quantum informatics, it brings together the ideas from classical information theory, quantum mechanics, and computer science. I'm assuming almost everyone here is known to the terms information theory and computer science. And after the wonderful introduction to quantum mechanics from Prashant, it is safe to say the basic definition of quantum mechanics is clear. So in quantum informatics, which is also known as quantum information theory, various theorems and techniques are finding their ways, like group theory, probability theory, and quantum statistical physics. As Prashant also told about the probability, how it is 50-50% probability about it is up or it is down, in which state it is. In classical informatics, we used to use discrete mathematics in the form of strings of zeros and ones, which are known to us as binary digits. Those are used for processing tasks such as storage and transmission of information. But in quantum information, instead of bits, quantum states are used as a basic element for the study of how such tasks like storage, transmission of information can be accomplished using quantum mechanical systems. There are various ways to use quantum states, such as nuclear spin, motion of trapped ions, photons and optical resonators. Every way has its unique way to advantage future technology. So, yeah. Talking about quantum states, which are known as qubits, as I mentioned, quantum states, those are named as qubits in quantum systems, which are the basic building blocks of quantum information. Unlike classical bits, qubits can be measured in different states at the same time. The classical bits are only 0 and 1, but they can be in various states. till they are measured.
Just a quick example, if I may. You see this
Yeah.
ball, it's a block sphere, what you see out there. So the block sphere basically states that every point on this ball can act as a pointer for a qubit state. When you measure it, it becomes one state, whether 0 or 1 in classical. But to show it, every point in the ball can become one state. And that's the beauty. Now you can calculate your algorithms across so many points of the state of a qubit in one shot, parallelly. And then you take a measurement and it brings you back to actually what you want. Thank you, Jerry.
Yes. So, as Prashant said, there are basically three main aspects of quantum information theory: quantum cryptography, teleportation, and computation. So firstly, quantum cryptography. Everyone must have heard about QKD, quantum key distribution. It's a well-heard name right now. They are working on the principle of Heisenberg. Prashant has mentioned a lot, best examples, I'll say, about them. And it provides secure key exchange in the existing classical network setting. They are not hindering the classical network setting. They are not hindering the models. They are providing security through the quantum mechanics principles. And quantum cryptography works on the principles, as I told, and promises to secure the network from quantum as well as classical adversaries. So, going towards the teleportation, Prashant has told us about two dices. If one is one side of the universe and the other is on the other side. So I can take an example of, we almost everyone have seen in the sci-fi movies, when a person is transported from one place to another, just putting in a vessel. We all must have paid attention to that part. It fascinates us. Yes, that happens due to the property of teleportation. As Prashant mentioned about the EPR, spooky action at a distance. It is happening. Also, the experiment was done by the Wolfgang group at the University of Calgary. It was an experiment done within the 6 kilometers between University of Calgary and the City Hall of Calgary. They have tested and sent photons, and actually that experiment was a success. They have sent photons, not persons right now, but if I may be optimistic and looking towards the future, persons will also be sent like this. So moving forward to the quantum computation, which is working on the property of superposition. Here, I'll recall my favorite example of a maze. Everyone have seen that part where you have one entry point and one exit. If you enter, you take left or you take right. If you go on the wrong way, you have to come back to the starting point from where you have taken the path, and then again have to choose the other path. We all must have loved that in our childhood or even right now. But if I say you that in using the quantum computing, you can go in both paths, on left side and also on the right side, and cover the whole maze and then can exit in one go, rather than trying left or right at every point. Yes, that is the power of superposition. It can do this. And it is the actual parallel computing. We used to use this concept in classical systems. We call that parallel computing, but quantum mechanics is actually providing it. Quantum computation is providing the power of parallel computing. So, after considering huge aspects of quantum information, there are definitely some benefits, like information remains inaccessible till it is measured. As Prashant said, in a ball of sapphire, we have a lot of points. If you will measure that, you will receive the value. But till you have not measured it, it has a lot of points, a lot of values at the same time. And it's a huge benefit for quantum cryptography and other protocols. As in cryptography, we need to encrypt the information. We need to keep the information hidden from the outside world. And if it can't be seen during the travel time, and it can only be seen when it will reach the point, then it's the best thing for quantum cryptography. And it follows the laws of physics instead of classical cryptography, is difficult mathematical calculations. Everything is working on the laws of physics, as Prashant has mentioned them wonderfully. So even the property of entanglement, the spooking action at a distance, I love this part, spooking action, is also providing the possibility to compute some incomputable problems, such as factorization and certain simulations. If we all know, if people are here from the security background, they must know that two factors are taken, and it is said that those prime factors cannot be calculated, but using quantum cryptography, they can be. If a quantum computer is coming into existence in coming like 50 years or 60 years, but someday it will, definitely will. So here, no doubt, there are many benefits of quantum information, but it has some challenges that many researchers are working hard to solve. But I'll say it's all about opportunities and threats at the same time. When any new field is emerging, like quantum computation right now, quantum cryptography has been achieved, no doubt, with the help of quantum key distribution, but still, it requires some more developments. It requires some sources and detectors. There is a concept of blind cryptography in quantum, but it is far away from reality right now. But when the quantum computers will come into existence, those things can actually happen. Yeah, I was talking about quantum computer again and again. No doubt, all the efforts are being poured to make them a reality. People are talking about quantum networks, quantum computers, but they are far away. Right now, everyone is trying to make the reality, and they are providing the quantum algorithms and quantum power over the classical networks so that we can be a few steps ahead of our classical adversaries. Just in the same way, some computing problems for proving quantum computing is advantage are less in number right now. Last but not least, quantum softwares. Even my research group in the University of Calgary, where I'm working right now, many among us are working hard on quantum software to make it a reality. And I can safely say that rather than 50 years, it will come into existence in 40 or 30 years. Let's hope for the best. Okay, so moving towards the next slide. I can say after clearing off some dust, I can safely talk about business application areas of quantum computing. As Prashant has shown us this graph, where he showed the Murray's law, where we are standing and what's the future, the quantum computing. It is high time for something new to come and perform some miracles. And what can be best than something that is of physics, that is philosophy, and that is computer science. Nothing can be better than quantum here, I will say. No doubt, it's been more than 25 years and researchers are working and publishing great work on quantum computing. If you'll Google it, or you will see a lot of research papers and a lot of experiments. Even in last February, an experiment was done on entanglement swapping even. So even business people are looking forward to something new, something revolutionary where they can invest and look for the future. Just like the D-Wave, if you people have heard about the Canada's based company, D-Wave, they have provided a quantum annealer that claims to provide various applications. For instance, financial portfolio optimization, logistic planning, traffic congestion, fault detection, supply chain management, scheduling, and many more. Along with this, in quantum machine learning, even quantum computing is providing a lot of benefit. I can say even less training data set can help to train a model perfectly, unlike classical systems. Using quantum machine learning, it's a huge benefit. There are also other potential application areas like security. I have talked about quantum security and is providing a lot of benefit in that area. Even I am also working in that area. I'm working on classical networks and quantum. I'm trying to mingle both the parts at a point. And there are also quantum sensing that is doing wonderful in oil and gas sector. I'll not say it has provided results right now, but researchers are working towards it, and we are looking towards something beautiful because Alberta is a oil and gas state, I can say. So work is going on. We are waiting for some wonderful results. So after this, we will like to include some of the Silicon Valley's giants working towards providing platforms for various business applications. Firstly, G-Wave, as I already mentioned, various, potential benefits they are providing. They are claiming it. D-Wave is providing access to their special purpose quantum annealer. They are providing quantum systems, client services, application development tools. If they are for developing quantum solutions for various issues. So one of the reviewers even said that the computation that used to take 25 days is taking seconds. Isn't it interesting? So I guess we are just have 5 minutes. So Prashant, can we just have a look on the companies that are here and move towards the question answer session? So Google.
Yeah.
Yes. So Google is also claiming to provide a fault-tolerant computer. And after that, it has its platform also, ExxonMobil. They are partnering with IBM to provide oil and gas sector a transformation. And after that, IBM Q is a huge network, and they have their 50-qubit quantum computer, and they have provided the access. If you want to try, you can register, you can submit your problems, you can get your results. It's very wonderful. And after that, Apple, they in iPhone 13, in iPhone 12, the chip they have provided, as Prashant has mentioned, that technology can only be possible through quantum. So following by this, the next Microsoft, even they have provided the access to the cloud for performing application optimization and everything. So this is end from our side. We are open to question answers.
Absolutely fantastic. Thank you so much, Prashant. Thank you so much, Cherry, for that wonderful session. We've got some questions. Okay, actually, one question I can see in the Q&A. I'll go over to chat to see if you have more questions there. But the question from Parul is that with the evolution of quantum computing, what would be the impact in the world of cybersecurity? Can we say quantum computers will be a threat to encryption algorithms?
So I'll take a stab at it, and then maybe Cherry can also speak to it. So this is fundamental to human nature. Wherever there is a positive, there is a negative. So if quantum computing is providing you the capabilities to secure information, as we talked about in encryption, by breaking the laws of physics, which is not technical, it's not possible unless you do it using the Heisenberg principle. So you do quantum key distribution through classical networks. That's the part of quantum computing which is providing kind of foolproof security, if you will, at this stage, because this is where the laws of physics are being managed. There is other aspect of it. It doesn't stop the bad guys or the adversaries to also use quantum computers to attack either classical networks or even quantum networks. So we have to see how an adversary / a security aspect of it would play out. But I mean, certainly, Cherry, if you have anything to add to that, go ahead.
And Prashant is very much right here. We can't ignore the fact that quantum adversaries are out there. If we are looking forward for the quantum computers, then obviously, if we have the quantum computers for high computation, then the adversaries, the hackers, the bad guys do have those quantum computers. Then we should look forward for something secure. That's why so much is happening in quantum computers, and we are providing more in quantum computers through quantum algorithms and security techniques. Yeah.
Great. Thank you so much for the response to that. We do not have any other question. If you have questions, please post it on Q&A. We have just about a minute, but lots of thank you. Great presentation, great information from the audience. Absolutely.
So I would like to just put a couple of comments since we have a minute to fill while questions can come in. As we went through the presentation, and happy to share some links out there. There are options for developers on this B-Sides call, or folks who want to go dig deeper into not just understanding the philosophy. So Microsoft has its platform on doing coding and development. Google has its platform. I think you can register online and do that. They are providing you the quantum algorithms, the logic behind it. I think Google uses a protocol called CIRQ, C-I-R-Q, or the language, to be able to actually mimic quantum algorithms out in their classical networks or on their system. So I would encourage folks on this call not to take this presentation as, oh, what is coming down the pipe, let's wait for it. Go check it out. Go check out, what Azure is doing on the cloud side for quantum computing. Go check out what Google is doing, what IBM is doing in this space, what ExxonMobil is doing. These are some very fundamental, practical things happening today, which folks like us can bring on board and, maybe act as stewards for society. So thank you.
Great. Thank you very much. And that's it. We've come to the end of this session. Absolutely. Thank you for having you, Prashant and Cherry. Thank you for supporting us and giving us a wealth of knowledge on this topic. See you on the other side. Bye-bye, everyone.